As a continuation of topics covered in differential calculus, let's talk about optimization and min-max problems. So there are three simple steps to these. The first is to model and make the equation of whatever the problem that you're given. Model and make equation. The next step is to take this equation and take the derivative. So derivative, take the derivative of the equation and set it equal to 0. And set equal to... Alright, so that's the next step. And the third step, well, this step makes sense. Let's just go into that first. Because if you have a function and you model something, and you set it equal to, the derivative equal to 0, that means where the slope is 0. So that would be here, right? When this function has its absolute maximum, or when it has a maximum. Well, that will be when the derivative is equal to 0. And the same works for minimum. So when you're doing min-max problems, you will know the minimum and maximum points by setting the derivative of the equation to 0. And the third step is to solve and interpret your results. So these are three basic steps: model, take the derivative, and then solve. So let's start with an example. So you have to make a rectangular box. So here's the problem example. Make a rectangular box and from a 8 by 15 inch piece of cardboard. And you're going to make this box by cutting 4 congruent squares from each corner. You have to cut 4 congruent squares from each corner, and you want this box to be the maximum possible volume. So what is the dimensions of this box? What are the dimensions? So for the maximum volume. Max volume. So let's start solving this equation. So first let's model it, and let's draw a diagram, a quick diagram that will help explain what exactly is going on. And this is an 8 by 15 piece of cardboard, and you have to cut 4 equally sized squares from each side. So when you're going about this, you want to think about it more algebraically, and you can say that each square has a side length of x. Right? So all of these squares will have side lengths of x, so they're all x by x squares. And then you know that the volume, so now you have to make an equation. That's the first step, right? Making an equation. So for the volume, you know that the volume formula is length times width times height, right? So volume is equal to length times width times height. So you can see the length here of, so basically, you're making a box, and this is the base, and this is the height right here. If you want to visualize you folding it up and making an open box. So the length will be this, right? So it'll be 15 minus 2x, because you're subtracting an x from each side here, right? And that'll be this length. And then the width will be 8 minus 2x, because again, you're subtracting a length of value x from each side to get this. And the height is just x, because you're just folding this in. So the height is x. So now you have, in effect, modeled this problem and made an equation. So the next step would be to get the derivative of this equation and set it equal to 0. But first, let's simplify this a little bit. So if you do multiply this out, you do you do FOIL method and you get 120, that's 15 times 8, minus 30x. I'm just going to solve it out because it's just FOIL method. It's 4x squared and it's times x, so then you get v, volume is equal to 120 x minus 30x squared minus 16x squared plus 4x cubed, and you get volume is equal to 120x minus 90, so now, so this is just simplified. And you can take the derivative of this, right? So v prime is equal to 120 minus 60x minus 32x, because again, this is just taking the derivative, and derivative of 120x is 120. You can separate these out because this is just the sum, right, of derivatives, and you can separate them out into individual things. And this is 2 times 30 is 60, then it's n minus 1, so it's just x. Again, the same thing here, 32x plus, and 3 times 4, 12x squared. And you can combine like terms. V prime is equal to 120. And actually, we could have done that earlier over here, but it shows to do it here. So 120 minus 92x plus 12x squared. So now we have v prime, and this is the derivative. So we've just completed the second step, or first part of the second step. We've gotten the derivative. Now if you set this derivative equal to 0, and then we'll move on to third step, which is to solve. So let's take this derivative, and let's set it equal to 0. So 120 minus 92x plus 12x squared is equal to 0. So in solving this, fortunately you have to go through the quadratic formula, and you have to do the minus b squared plus or minus the square root of 4a plus or minus the square root of b squared minus 4ac over 2a. So you get 23 plus or minus the square root of well, actually first let's take a different route. Let's simplify this and divide each of these terms and the other side by a common factor, which in this case will be 4. So you divide everything by 4 and you get 3x squared minus 423x plus 30 is equal to 0. And now you can solve it, and you can use the quadratic formula. So it's minus b plus or minus again b squared minus 4ac over 2a. So it's 23 plus or minus the square root of this squared, which is 529 minus 4a 3 and c all over 2a, which is 6. And if you solve this out, you simplify it after a while, and you get x equal to 23 plus or minus 13 over 6, which is either equal to 6 or 5 over 3. So when you take this up here now into this problem, and you put 6 and 5 over 3, if you see which one works. And if you have 2 6's here, that'll be 12, and 8 minus 12 is a negative number. You can't have a negative side. So that clearly eliminates this 6. So you know the x here has to be 5 over 3, right? So now we just plug in this into here, this 5 over 3 into the x, and we can get the dimensions. So the dimensions of this will be 15 minus 2x, so 15 minus 10 over 3, and 15 minus 2x is 15 minus 10 over 3, and 15 minus 10 over 3 is 11 and 2/3. So the length is 11 and 2/3. The width will be 8 minus 10 over 3, which is 14, which is 4 and 2/3. So 4 and 2/3. And the height is just x, which is 5 over 3. And these are the dimensions of our rectangle. I will be doing one more video after this also, and it'll just be an example of another min-max problem.